All right, so let's go ahead and continue from last time. Today, today we will finish up with our performance analysis, and then hopefully we'll continue on to basically the next step, which is OOP and some more, I guess, more about pointers. Okay, it's only 80 and not 84, so that's a benefit from last time. So let's go ahead and do a quick refresh on what we went through last time. We talked about how we do analysis and that we're doing, or how we're going to do our theoretical analysis. We talked about just everything having a time unit of just one, namely assignment, Boolean expressions, adding, etc., etc. And we went through a couple examples, and we ended up with this example. So to refresh, to make sure everyone still remembers what's going on, we're going to go ahead and calculate the cost of this piece of code. So I know, first right off the back, let's start asking questions. What's the cost of C1?
1.
All right, 2,
1.
3, 4, 5, 2, or I mean 6. We'll give you, that's the answer. 7 is 2, and all right. So then what's the cost of the inner while loop? One instant, yeah, one run is 5. It runs how many times?
N times.
N times. So the total cost is?
5. 4.
No, it's 5N, because that's how many times it costs. Because each time you run it, you have to do assignment, add, test the Boolean, so that's 5. But it's not just 5N. It's 1 plus 5N, because the first time the loop starts, you have to do the test. So even if N was 0, you still had to pay the cost of N. Whew. All right. Let's see, how far are we? Oh. Executes N times. How many times does the outer loop execute?
N times.
And what's the cost of the outer loop? Well, 1, 2, plus the cost of this, which we calculated as what, 1 plus 5N? So 3, 4, 5. So it's 5 plus 5N, all times N. Hey, there it is. You can math it all out without, math it all out. Yeah, sure, math it all out. You get something similar to this. All right, there's something very important in this final formula that you need to recognize. The n squared is the largest term. Just keep that in the back of your mind right now, and you'll find out in a bit why that is so important. Hi, everyone good? Nice refresh. Back on Wednesday. Perfect. Okay. So comparing algorithms. So the idea is if we have two competing algorithms, we're trying to evaluate the performance. How do we determine which one's better? I mean, we went through this whole cost function, which will give us a formula at the end. But how do we determine when one is better than the other? Well, right, we can measure algorithm's time as a function. All right. So if algorithm A, let's jump here, requires 5 times n squared time units to solve, and B is 7 times n. Do you know which one's better?
7 times N.
Why would 7 times n be better?
Because it's simpler.
It's simpler? Simpler. Okay. Yeah, it's probably simpler to code because it doesn't have any extra loops. But why is it better time-wise, I guess?
It won't loop through as many times. Because there isn't a second loop.
There isn't a second. Okay. Well, if n is 1, which one's faster? Yeah, A is actually faster in that one. But if n is 2? B? Yeah, no, you're right. You're right. And then for every value greater than 2, I mean n greater than 2, it's also going to be B. What's important, the reason why this was chosen like that is we really care more about the growth rates. I mean, 5 versus 7 on your computer, you don't really care. Unless that extra 2 is really a crazy operation. In general, it's not. So you don't really care about those minor, very small differences. You care more about when it gets to very large numbers. And that's why we talk about the growth rates. So here's another one. Which one's better? Actually, hold on. If I ever ask the question, which is better, there is only one response. It depends. Again, on n, because if n is small, or very small, then the first one is actually faster until you get to, what? Is it 8? 8 is when the cutoff happens. And then actually the other one explodes. Hopefully this makes hopefully these numbers make some sense. So start off, the first one has some overhead to get it basically ramped up. The other one is okay until you get to about 8, and then it just starts exploding in complexity. Well, what happened? So I'm going to take what happened to this function over here, because notice this one, I mean, it gets bigger and bigger, but this one, it just starts, I mean, this is a order of magnitude almost. What's happening to that formula? Let me bounce back. I'm taking this formula right here. I'm copying over here with this number, and then I'm just going to evaluate this term right here. So this term is the only one at the end. And then on this column, I'm showing what percentage of the total this term is taking up. All right, so you got the formula, you got the one term I chose, and then the percentage of how much that one term is taking up of the total. Notice as n gets large, it quickly approaches 100%. So one term dominates the others. This is not just a coincidence. This is going to happen all the time. This implies you really only care about the dominating or the largest term, because in the end, when n is large enough, we only care about what that's going to do. So as n grows, some terms dominate more than others. For example, notice that when I say terms, talking about, you add your different terms in here. So here's an n squared, an n, a constant, and then a 3 to the end. So those are the different terms I'm talking about. If you go over here and you look, I made a quick little chart. That was kind of an estimation for some of these. Basically, if you have a log n, log base 2, it grows actually very slowly. Notice that when n is, what, 100,000, it only takes 16 units in order to find it. Of course, when n is n, it takes the same number as n. See, n log n grows a little faster. N squared is definitely significantly faster, so is n cubed. And then what happened here? Huge. Does this make sense what I'm pointing out here? Here's the ordering. 1 less than log n, less than n times log n, less than n squared, less than n cubed. Of course, I'm avoiding a couple. You could have into the 4th, into the 5th, or into this n squared times log n. We could start combining all these if we wanted to, but I just want to give you some of the most important ones. Also notice I did strictly less than. And when I say strictly, I'm talking about when n gets significantly large. AKA when you're over here. Oop. Okay. So now we're going to talk about big O. So beforehand, I've just been talking about the dominating terms. Now we're going to talk about big O, which is basically all it's saying is we really only care about the dominating term anyway, so just ignore the rest of it. Y'all haven't taken discrete math, have y'all? Go ahead. Oh, I like them using comments. Yeah, so if you have one, please share it with the class. But if you don't, I understand. It's okay. So with big O, we really would care about the largest term. Y'all haven't taken discrete math, so this part is probably somewhat confusing, talking about growth functions. And I'm going to skip this because you haven't taken discrete math. Well, we'll talk about this. I take this back. I'll read this real quick, and then I'll show you why it's easy. If an algorithm requires n squared minus 3n plus 10 to solve a problem, if constant k and n n sub 0 exists such that k times n squared plus n0 is greater than that for all n and all 0, then we say that the algorithm is of order n squared, namely if k is 3 and n is 2. All right, somewhat confusing. But the idea is that if you see this function, you know that it's big O of n squared. And this is the mathematical way to prove it. You haven't just taken discrete math, so I can't require this of you. But luckily, it's actually not that hard. It's really a game of spot the highest term. So for example, the first one is n to the cubed. Why? Here's the highest term. It's right here. Notice that big O chops off the coefficient in front of it, because we don't care so much about that either. It's really just what is it going to grow at. This one is 3 to the end. Note, oh, these make sense? It can get somewhat tricky. For example, if you don't multiply everything out, then you may it may not be obvious right off the bat what it is, but you multiply it out into the cube, or into the third, sorry. And then next one is n times log n would be the largest term. All right, bless you. Yes?
So how would you know that n times log n is going to be bigger than like n cubed or something, if that wasn't there? Like, how are you supposed to tell which one's bigger to put in the parentheses?
Oh, in here?
Yeah, like if you had...
So you want it to always be in this formula where you have term plus term plus term plus term, right?
Yeah.
So, aka take this, multiply it all out, distribute everything out. Don't try and clump it together, because if you did that to the bottom one, you'd have 10n plus n log n plus n, and then you could easily tell that it was n log n of those terms.
But what if the n at the end was like n cubed?
Then it would be n cubed.
But how do you know that's bigger than the log?
So I have set down and showed you some numbers. We don't care about the small n. Notice that as n becomes large, n cubed produces a higher number than what's n log n. And notice that that's actually pretty consistent. Yeah, that's consistent throughout. And if I were to graph functions, I could show you quickly that n cubed is always going to be larger than n log n. Somewhat empirical. When you take discrete math, actually, you'll take discrete math and then you'll take algorithms, and this will make more sense. Okay, here's an explanation. Maybe this will help a little more. O of 1 means that it's constant and does not matter the size of n. By the way, when I say n, I'm talking either about what's in that for loop or maybe the size of your data structure, how many elements are in it, or some other type of parameter. O1 says it doesn't matter how big your data structure is, it's just going to take constant time. And these are the best algorithms. If everything was O of 1, well, that'd be kind of scary because then encryption would not work. But anyways, if everything was O of 1, then our programs would run really fast. Log n is still actually pretty good. It's logarithmic and increases very slowly as the problem size. O of n means it's a linear correlation. As your problem size increases, your algorithm size, time increases linearly. N log n, basically you multiply the previous two, and that's how long it takes. N squared is going to be quadratic, n cubed is cubic. By the way, there is a jump between n cubed and 2 to the n. Namely, if your algorithm is 2 to the n, it's not going to run unless n is very small. When I say it's not going to run, I mean it'll not finish in your lifetime here on Earth. I'll put it that way.
How often does code get so messed up that it ends up being of that big O anyway?
It happens. I mean, hopefully your code you write most of the time that doesn't happen, but oh, it happens. It'll happen many times. And we'll have problems in class where it just happens. And you have to be a little more careful. For example, there are problems where, to the end, there's the, have you done travel? Yeah, you haven't done traveling salesman. So, you know, you have Google Maps and you pick 2 points and it shows you the shortest path between 2 points, right? What if instead of doing 2 points, you give it 100 points and you want to know what the shortest path is to visit all of those? That's an 2 to the n algorithm. So it does come up. Okay, let's do some practice. What's the big O of this? N. If you did all the costs, you know, all those times n plus the other ones, notice here, this is why I wrote out in the slides that you just add up the costs because they're constant, because in reality we don't care. That's just how it is. So it's a times n plus b, which is big O of n. All right, how about this one?
N squared.
N squared. Why is it n squared?
Because there's 2 loops.
Yeah, there's a nested loop. So I'm just trying to be precise. You could have 2 loops or one after another and then be n plus n, which is big O of n, but if you nest the loops, then it becomes n squared. Cubed? You could, well, no, not k cubed. Your parameter is n in this one, because it starts with n, excuse me, and then j is going to go up to I, which is based on n, so half the time it's going to go to n over 2, so it's n times n over 2, and k is going to go up to j, and j, what is it going to be? J half the time is n over 2 as well, so it's n times n over 2 times n over 2, which is n cubed over 4, essentially. Or if you want to really math it all out, you could go crazy. But the fact of the matter, and the easiest way to help to see this, is that obviously this goes up to n. This is going to go to n over 2 because it's going up to I. So the beginning is just 1, and then towards the end is n. So we'll say n over 2, aka n, because it's big O. We don't care about that half. Same thing with k, actually. Since j is going to evenly flop around between 1 and n, it happens n over 2 times. We don't care about that coefficient of n, that coefficient of 1/2, so we call it n as well. You can multiply it all out, but we really don't care about the coefficient, so we just call it n cubed. You don't need to know the exact number of iterations to find out the big O. That's what's nice about big O. And we're going to use this a lot in class. I just wanted to give you all some good practice. Any questions on this one? Okay. Hey, look, recursion. What's the big O of this one? Well, I hope this erases. Anyone? It's a simple function. You're just, what are we doing? Hanoi. If n's greater than 0, you call Hanoi n minus 1 and then n minus 1 again. So, in other words, by the way, I'm not going to expect you to, well, I'll expect you to be able to understand or be able to recognize this, but not fully understand it. I'll put it that way. So each call to Hanoi based on n is equal to call to Hanoi of n minus 1 plus another call to Hanoi of n minus 1, right? And that's done until n is 0, right? Yeah, here we go. So in other words, h of n equals 2 h of n minus 1. Or 0 if n equals 0. Y'all see that? All right. So what is this? Well, fortunately, y'all haven't taken discrete math. But when you do, discrete structures, so that's what it's called here. You'll be able to solve this recurrence relation hopefully pretty quickly. Well, let's go ahead and do some numbers just to give us an idea. So if n is 0, let's do this. H of n, and then n equals 0. The answer would be 0, because it's 0 here. If it's 1, it'd be 2 times n minus 1. Or, yep, I did 2. Well, did I really put 0? I'm missing something. Whee! That's what we're going to do, plus a constant. Some constant of how long it takes to do the calculation. I totally forgot to do that. So 2c, and then if it's 2 here, it's going to be 4, right? Because it's 2 times that previous one. 3, 2 times the previous one. 4. Hey, wait, have you seen the pattern yet? Oops. What are these numbers? Anyone know what that is? Or can anyone recognize?
That's factorial.
No, factorial.
Yeah.
Not factorial.
Exponential.
It's exponential.
That's close.
It's 2 to the n. Recursion is not always 2 to the n. I just gave you this one because this example is easier to see that it's 2 to the n. All right, so it's 2 to the n because every n we make 2 to n minus 1 calls. All right, you'll have to recognize this bullet point at the end for this class, but I'm not going to expect you to do this, what's up there, where we'd have to actually do a proof by induction to show what we're saying is correct. We don't have time, or I don't have time to teach that. But do recognize that if a function or a function calls itself twice n minus 1, then it's 2 to the n. By the way, what if it calls itself 3 times n to the minus 1 each time? It would be 3 to the n. And then if it was 4, it'd be 4 to the n. 5 is 5 to the n, et cetera, et cetera. All right. Okay. How are we doing?
Know what comes next, but I hate it.
GNU plot? But it.